I know what you're thinking. You're thinking it can't be this boring to just use the geometric series test for every single rational function. There's got to be something a little bit more interesting. Well, I'm glad you asked because examples 6 and 7 switch things up just a little bit, just enough to make things a little bit more interesting. So I think we might have seen somewhere that the sum from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r, provided that the absolute value of r is less than 1. I think someone told me that once. So if I'm looking at this fraction right here as the fraction we're trying to convert into a Taylor series, then I'll notice that a is equal to the numerator of 1, and r is now not equal to x, or negative x, or x squared is now equal to 2x. Okay, whoop-de-doo. That's not really all that exciting, is it? Okay, well, let's just see how this changes things. Well, we know that this is still from n equals 0 to infinity. We're taking the sum. A is still 1, so that's not very exciting. R is now 2x instead of 1x. So if I'm going to raise r to the n, I want to make sure that that 2, super important to make sure that 2 stays inside the parentheses. Okay, so sure, that's not so surprising. And we get 1, and then when we raise this to the first power, we get 2x, and when we raise this to the second power, of course, we get 4x squared. We raise it to the third power, of course, the 2 cubed becomes 8. So we have to remember to cube not just the x, but also the coefficient. Okay, so that's marginally interesting, I guess. And we also have to remember that interval of convergence. So remember that this is true provided that r is less than 1. Well, r is 2x, so 2x, the absolute value of 2x has to be less than 1, which means that the absolute value of x has to be less than 1/2. Okay, so this is a little bit interesting because now we're seeing that the radius of convergence, is no longer 1. In all of those previous examples, the radius of convergence was 1. Now the radius of convergence is 1/2. We still don't have to worry about checking the endpoints. That's what makes this stuff so beautiful. That's one of the things that makes this stuff so beautiful. But we can see how the interval of convergence might change. Now, example 7 looks innocent enough, but there's a pretty nasty trick here that we have to be cognizant of. So we're going to start by remembering this thing that someone once told us, that the sum from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r, provided that the absolute value of r is less than 1. And we're going to compare that to the fraction 1 over 4 plus x. Wait a second. This is the first time I've seen something other than 1 right here. That 4 bothers me because while a is something that can change, we can change that to 1 to x we did earlier, or 7, or anything at all. A can be whatever. R, likewise, can be whatever we want it to be. But this is a number. This number can't change. We can't just change that 1 to a 4. We're going to have to change this 4 back to a 1 somehow. So how's that going to happen? We can't just go around taking a function and say, I just don't like that 4. I'm going to change it to a 1. Because that's going to change the function. So what I want to do is I need to actually do an algebra step that's allowed. In other words, like if we have a fraction, we can multiply the top and the bottom times the same thing. The same thing in this case is going to be 1/4. Why? Because 1/4 times 4 will give us the 1 that we absolutely need. That's the only number in this formula. Everything else can be whatever we want it to be, but we've got to have the 1. So when we do that, we end up with a 1/4 in the numerator. We have a 1 plus x over 4 in the denominator. Of course, we're not going to forget to distribute. That would be silly if we forgot that. And if we say, well, we have to have that minus sign, well, we've seen that before. We've seen a plus, so we can change that to a minus, no problem. Instead of adding a positive, we'll subtract a negative. And suddenly, we no longer have, sometimes my Control-Z doesn't want to work. Suddenly we have a fraction in the form a over 1 minus r. Okay, fantastic. Now we are cooking with gas. So that means that we know our A value, we know our R value, and that's all we need, right? We know that this equals the sum from n equals 0 to infinity of A, which is 1/4, times R, which is negative x over 4 raised to the n. And if we're going to write out the first 4, because that's what it asks for, the first 4 non-zero terms, like all of these examples have done, we'll let n equal 0, we'll get 1/4. And if r equals negative x over 4, we'll just multiply everything, every previous term by negative x over 4. 4 times 4 is 16. Negative times negative is positive. X times x is x squared. 16 times 4 is 64. Positive times negative is negative. X times x squared is x cubed. 64 times 4 is 256. And we'll continue to add and then subtract, alternating because r is negative. All right, what is the interval of convergence? Well, we have to say that the absolute value of our r value is less than 1. So that means that this is going to converge provided that only if the absolute value of x is less than 4. So this is kind of nice. We now see a bigger radius of convergence than we're used to seeing. So I can't resist. I'm going to go ahead and Desmos this. I've got the fraction 1 over 4 plus x. Okay. So 1 over 4 plus x. 1 over 4 plus x. All right. And we've got our Taylor series was negative x over 4, right? And we take a look, let's hide this for now. We take a look at the red versus the green, and they seem to fit pretty well. Maybe we can see some divergence over here near the vertical asymptote. So maybe I'll bump this up. I'll play with fire here and change my degree 20 polynomial to a degree 40 polynomial. And that actually worked pretty well. Notice that the interval of convergence is way bigger than that tiny little -1 to +1. We're actually going from -4 to +4. So this is a much more effective series because it matches our function, right? This series matches the function. The red matches the green for a much bigger area, a much bigger domain. And we can mess around with this. You might notice, this is always going to be the case, that the interval of convergence goes from the center all the way to a vertical asymptote, and then the same distance to the other side. So that's a nice little trick that you can keep in the back of your head. But anyway, there you have some graphical evidence that I'm not just making this up, that I'm in cahoots with Desmos, and Desmos is just faking this. But I don't think it is.